All right. Our next speaker, also an LRGF fellow, Brianna MacNider. She's at the University of California, San Diego, working in the field of aerospace engineering, and did 2 residencies at Los Alamos National Laboratory.
Hi, so I'm Brianna. I'm going to be talking today. The title of my talk is Toward High Strain Rate Inverse Design via Experimental Exploration of High Strain Rate Dynamic Behavior of Materials and Structures, which is a little bit of a mouthful. I'll get into it. I'm going to be talking mostly about the work that I did during my residencies today. It is motivated and an extension on the work that I was originally doing for my dissertation. Okay, so my motivation, I'm sure a lot of people here are very aware of motivation for looking at high strain rate behavior. There are a multitude of reasons to do so, but I'm going to give maybe a little bit of a different type of motivation for looking at high strain rate behavior. It's related to my dissertation work that might be slightly different from what you're used to. So a large part of my early dissertation work looks at basically using topology optimization to tailor nonlinear structures for desired nonlinear constitutive behavior, with the idea that we could then take these structures and then make them very small and put a bunch of them together and sort of make a bulk material that has tailored nonlinear properties, with the goal of being able to tailor waves moving through these sort of effective designer materials. And so shown up here is a couple of papers from this early dissertation work in which we do this. On the left is our sort of quasi-static proof of concept. On the right is where we start bringing some wave dynamics into it. But the key point with this is that the optimization approach relies on quasi-static deformation, or if you're going into dynamics, it only really works if your dynamic regime is low enough strain rate that the deformation mechanisms are essentially the same as the quasi-static regime. So we would like to be able to move up into higher strain rate regimes to go into things like shock and higher strain rate impact mitigation and things of that nature, but it doesn't work really well at high strain rate regimes because the physics are very different. And so we want to, the motivation for my residency work was sort of be able to explore some of this higher strain rate behavior of materials and structures to better inform optimization attempts going forward. And that's a sort of a huge problem, so it's not quite all wrapped up with a nice bow in one project, but at least sort of gives us insight into the types of things we need to consider in the path forward to take to inform this work as it goes forward. So I'm going to talk about 2 distinct projects that I did at my 2 different residencies. This first one is in situ spallation of metals. So for those of you who are not familiar, I'm just going to briefly go over what spall is. So spall is a failure mechanism that can take place in dynamic and very high strain rate situations in which when you have sort of a high strain rate impact, as demonstrated on the left here, you end up propagating a shock into your sample. This shock also propagates back into the impactor, hits the free ends, and then rebounds back as a release wave. And then where these release waves cross, you get a plane where you have a region of tension, which creates voids that nucleate and then sort of grow and coalesce together, and you end up with failure at this point as things sort of rip apart. And so why this is interesting is that predicting and modeling damage in this regime can be very challenging due to the time and length scales involved. There's also a lot of assumptions. There are a lot of attempts at sort of analytically trying to predict what damage looks like in these regimes, and these involve a lot of assumptions in regards to how the voids nucleate and grow. Models often have to be tuned with experimental data for specific materials and loading scenarios. So if you have one type of microstructure, it's not necessarily going to behave the same way under these conditions as a different type. Common investigation methods have included taking recovered samples from experiments, and then also taking sort of PDV laser probes or MD simulations. But the problem with all of these is they don't actually give you an insight into what is happening inside of the material as this failure is happening. So it's sort of just after the fact or sort of from the boundaries. We don't really have a good look at what's happening inside. And so that was what this project was about. I had the opportunity to, through this residency work, look at some data that was taken from an in situ look at spallation happening, which I'm going to go over. This sort of allowed me to have a a good introduction to this sort of very high strain rate shock regime and some of the image processing techniques that I have used in later work. So the experimental setup, this was done at the dynamic compression sector. Essentially what's done is we were looking at magnesium in this case. There were several different types of magnesium of varying microstructures, and these samples were made and then placed inside of this gas gun, were struck with an impact at very high strain rates, and then there's a series of X-rays that can come through this window and sort of X-ray through the width of the sample during the spallation event. And the neat thing about this is that you can take multiples, so we can get 8 frames, 153 nanoseconds apart, so we can get sort of a series of snapshots through time and sort of watch this process form and take place. So this is a set of this data from these experiments. This is a sort of post-process to sort of clean it up and look nice and all of that, but you can see this is time-resolved data in polycrystalline magnesium. So each of these snapshots is a different time from left to right and top to bottom. The time is moving forward, and then in each of these snapshots, the shock is coming from the right-hand direction. And you can see this sort of beautiful spall plane form in the middle, and we have these fantastic, very highly resolved images where you can see it start to form, and then you can watch all these voids grow and eventually get to the point where they coalesce, and you have a huge damaged plane there. And so the fun thing about this data is it has a pretty high spatial resolution, and it has a pretty good time resolution as well. So this is actually the first time that we can have been able to sort of get this level of spatial and time resolution of this process in metals to be able to sort of directly image what it looks like. And I'd mentioned that the microstructure affects a lot the way that the spall propagation actually takes place. And so these are snapshots at similar times after impact of some of the different microstructures that we tested. So you can see on the top here we have a single crystal magnesium of 3 different orientations. In the bottom here we have an alloy and pure polycrystalline. And you can see that not only does the morphology of the planes look very different, you know, the direction that they've grown in looks very different, but also the amount of damage is very different. So for example, that top left one there barely sustained any damage at all, so it survived quite well, whereas the bottom right it has a ton of damage. And the fun, sort of super interesting thing about this work is because of the spatial and time resolution, we're able to sort of resolve individual voids at a certain length scale. There are ones that are probably smaller that we can't resolve, but at this length scale, we're able to pick out individual voids and using image processing, go through and sort of track a void from image to image, which is shown here. So you can see we've picked out a single void and then sort of track the way that its shape and size changes across images until the point where it coalesces with other voids and things get a little bit more complicated. But through this, we're able to actually directly measure the growth rate of these voids, which is something that up until now is either had to be done from sort of tuning models to match or post-motor analysis. So this is the first time we've been able to sort of directly measure actually how fast these are growing. And it is, you know, some interesting insights here is that not all of the voids necessarily grow at the same rate. Some of this could be from experimental issues, but it's there's a little bit of a distribution. So you can take either, you know, a single void growth rate from this, or you can take an average, or get a nice distribution that you could then use in your models to improve the damage predictions. And so continuing on with the image processing, basically what we do is we look at these X-ray images, and by looking at the intensity, we're able to say, okay, you know, where the intensity increases, the density has gone down, we have voids growing. And so in addition to tracking individual voids, we can use this to sort of get a global look at what damage across the sample looks like. So on the left here is an example where we basically went across the width of the sample in the loading direction and sum up the intensities vertically, and so we can get sort of a damage plane that we condense down to one line for each time. And so you can see at the top there, that's the orientation that did not sustain a lot of damage, and so you can see on the top left that has very, very low lines, and in the bottom left here, this is the sample that sustained a lot of damage, and you can see that this damage plane is much larger. And then in looking at these damage planes at each point in time, we can integrate under the curve to get sort of an estimate of what the sort of total damage in the sample looks like at that time quantitatively. And so these are plotted over on the right there for a bunch of the different tests that we did. And some interesting things to pull out of this is if you look at the slopes, basically these lines on the right, we could sort of call this the growth rate of the damage plane. But the cool thing about it is that it's not all necessarily linear. And so some of these curves, a linear line would fit very well, but some of them are very distinctly nonlinear, which means that the rate of damage growth changes across time. And then also sort of picking out some of the shapes of the curve on the left, the actual morphology of what the spall plane looks like, you can sort of get a quantitative look at how that changes over time. This bottom left one, for example, you can see there's a point in the middle where it sort of starts to have two peaks for a little bit before coming back together. And so this sort of time-resolved data is something that you really wouldn't be able to get a good look at from traditional measurement techniques. And so the idea we're hoping is that we can take some of this data and use it to sort of inform and tune modeling and simulation and damage predictions going forward, where you might be able to sort of get a look at the way that things are evolving over time with this technique and say, okay, well, it's not the same across the entire loading time. So that sort of wraps up this work. This was a great opportunity I got to do during my first residency. Talking about Project 2, which I worked on in my second residency and which we're still finishing putting the manuscript together for now. I wanted to look at sort of more architected materials, since the driving motivation behind some of my dissertation work is how to let optimization inform how we can change structures around to achieve the desired goal. We want to look at not just microstructure, but also sort of structured materials that have struts and beams and sort of larger geometric features that we could examine. And one thing we know about these types of structures is that as the strain rate is increased, you have fundamentally different deformation mechanisms that are engaged. So on the left here, you can see just some examples. On the top left there, this is a sort of more quasi-static type of deformation where you have a very nice global buckle as you deform the beam. And then as you start to increase the strain rate, you get some, in the center there, inertial effects where you have sort of localized buckling behavior, and then eventually you reach the shock regime where things just change completely. But we do know that even at these lower strain rate regimes, that the strain rate does actually affect the force displacement behavior of the sample. So on the right there, you can see some examples that there is a distinct effect, and sometimes that effect is only attributed to the material, but sometimes it is also attributed to inertial effects coming from the geometry of the lattice. And so this is something that we wanted to explore a little bit more. So the experimental setup we did here to do this is I employed one of the Hopkinson bars at Los Alamos National Lab. We picked 4 different just sort of standard lattice types shown there on the bottom. And so these were additively manufactured out of a soft polymer, which is also interesting because a lot of the works that look at similar things work with much stiffer materials and metals. And so this is maybe a little bit different than some of the other work people have looked at. We put this in the Hopkinson bar. As you can see on the top there, you can see where the sample is indicated along the bar. And the idea is that we then load the pressure chamber and then launch a striker bar, which launches a wave through the sample at a desired strain rate. And we also employed, with our strain gauges on each end, so you can get strain data. But in addition to that, we also put a speckle pattern on these samples and then put a high-speed camera pointed at it so that we could actually get the video of it deforming and then use digital image correlation to pull out the strain fields over time for how these were deforming. So I'm going to show here some videos of this happening. These look very slow because they're shot at 500,000 frames per second, but I promise it's actually quite fast. And you can see there's some sort of fundamental differences between the ways that the geometry deforms in each of these samples. So on the right here, this is some of that digital image correlation data that I talked about. This is a snapshot from each of the tests we did with the X direction of strain fields pulled out and then plotted on top of the deformed samples. And so you can see we tested at 3 different pressures across 4 different samples, and those pressures correspond to roughly between 1,500 and 3,000 strain rates. The goal here was that we wanted to sort of target a more medium strain rate with this, where we're not getting into very, very high dynamic effects yet, but we're definitely not in quasi-static. We're trying to sort of explore a transition region with these lattices. and bringing some insight from some of the things that we do in our lab with stress waves and metamaterials. We define this criteria over here on the left in that we wanted to look at where these regimes actually take place at. The important thing for informing the optimization is sort of predicting whether or not you're going to be in a more quasi-static regime or you're going to be in a regime in which inertia starts to take effect, or you're going to be even higher than that. And so, what is a good way to predict if you're going to be dealing with these effects or not? And so we define what we're calling a wave-dominated regime, which essentially just means that the dynamic deformation has been localized within the lattice, which means that you have the possibility to get inertial effects occurring as the lattice deforms. And so we define this as occurring when the effective wavelength, which is equal to the effective speed of sound times the time, is less than some characteristic length. This characteristic length can be either the length of your entire sample or the length of a single unit cell row within the sample, depending on sort of what level of localization you want to look at. So we do some math, move some things around, get this dimensionless parameter, and say that you should be in this wave-localized regime when this dimensionless parameter is less than 1. And we think that this is sort of important because a lot of other work that is sort of focused in this area has looked at only the strain rate, but the characteristic length scale and the material and how fast things propagate through the material also are very important for whether or not you're actually getting localized dynamic deformation. And so this is, we think, maybe more of a complete picture of the story. So this is some of these strain fields that I had talked about, but across time. And so essentially what we did here is similar in the last experiment. Across the width of the sample in the loading direction, the strain field was summed in the vertical direction, and then sort of compress it down to one line and then plotted. So red color here is early time, and then as you bleed into blue, it goes forward in time. And so you can see the impacts coming from the right edge, that you get sort of different spikes, different peaks of localization, depending on which geometry you're in. For example, this bottom gyroid lattice here was the most dense of all of them, and you could see it also has deformation that is sort of more distributed out across the sample and fewer peaks than the others. And if we take this and we pull out just the early couple of time steps, I believe this is the first 5 frames of each of these, you can see that this strain field deformation is actually localized initially at the right edge and then propagates across with time to the left. So this is a surefire indication that we are in a regime in which we have localization taking place, in which we might expect inertial effects to take place. And indeed, if we calculate or take an upper estimate on this dimensionless parameter for each of these lattices, they're well below the limit of 1 that we were looking at. And so this lines up with what our prediction was sort of expecting here. And as I mentioned, this is a work that is still in progress a little bit. Still happy to talk about it more if anyone has any questions. But one of the takeaways we're hoping to have with this is to sort of map out what these different behavior mechanisms in these different regimes look like, and do it in terms of our dimensionless parameter here, so we can have a better prediction of what effects we need to deal with in the optimization attempts at different conditions. And so you can see when you have to the right here a very, very high dimensionless parameter, you're very much in the quasi-static regime, and as you start to lower that, you enter some sort of a dynamic transition where the constituent material response starts to have some strain rate effects, but you're probably not engaging inertia of the lattice itself deforming because you don't have localized behavior yet. Eventually, as you go lower than 1, you enter a region in which you have wave-dominated behavior, in which their inertia effects start to gain importance. And then eventually, if you keep going very, very, very low, which is outside of the scope of this second project here, you will enter the shock regime where things start to change even more. So thank you. That's just a summary of the residency work that I was able to do the last couple of summers. I want to give a special thanks to both of my advisors, Nick Beckler and Alicia Kim, and as well as my residency mentors, Dana Dadelbaum and Saryu Fenson, and also just thank the fellowship. This is a work that I would not have been able to do without it. I did not have access to these types of facilities or data at my home institution. So yeah, thank you.